Hey guys, just going to run through these dilution slides in case you wanted to see them again. Sorry, I got to run back and forth to the computer. But I'm going to skip that first slide, the molarity practice, because it's basically the same as just what we went over with molarity. But we'll talk about dilutions today. So the basic idea here is that diluting something, or better known as just watering it down, is a common thing that chemists have to do because we often need lots of different concentrations of something. Maybe I need something that's really concentrated, maybe I need a solution that's not very concentrated, and it doesn't make sense to store all like bottles or flasks of solutions of a bunch of different concentrations, because that just takes up a bunch of space in the storage room. And so what chemists do is they keep a stock solution, which is highly concentrated. And if you need a solution that's less concentrated, you just take some of that stock solution, pour it in your container, and then dilute it with water down to the concentration that you need, or the molarity that you need. In order to do that, you need to know how to do the math. So we're going to learn the math because this is how chemists do it. So let's just jump in. Okay, so this is just a very simple starting example where I will have, let's say I have a solution, it is 85 milliliters of potassium hydroxide, and it has that concentration over there. And so if I water it down, if I add 10 milliliters of water, that it intuitively makes sense that I would get a lower concentration, right? I'm watering it down, I'm diluting it. Okay, so we want to calculate the new concentration, okay? Well, how do I calculate concentration? I use my molarity equation, okay? So concentration in terms of molarity, so maybe I should specify, but I mean molarity when I say concentration. Molarity is moles over the volume of the total solution, okay? So I'm gonna kind of go about this backwards. What would be the volume of my solution? Well, I started with 85 milliliters, I added 10 milliliters of water, and so it would make sense that my solution, my volume, would just be the sum of those two numbers. Okay, I'm gonna write this in liters, right? So 0.095 liters is the same as 95 milliliters. Okay, so I did that conversion in my head, just for those of you that are following along. Okay, and then in order to figure out this concentration, I need to know how many moles. Well, when I added water to this original solution, the moles of potassium hydroxide didn't change, right? If you add water, I'm not adding or taking away potassium hydroxide. So if I want to know how much potassium hydroxide is in here, I can just take my original solution and solve for the moles. Okay, so let me come over here and do that on the side. Moles is, if I rearrange this, moles would be molarity times volume. Okay, so the moles that I started with up here would be the concentration times the volume in liters, of course. Okay, so if I do that, let me go grab a calculator. Oh, here's one right here. So 4.5 times 0.085 means that I had 0.3825 moles of potassium hydroxide. Okay, and when I water it down, I still have the same number of moles, so I can just plug it in up here. So if I want to know what the resulting concentration is, all I need to do is take this number of moles divided by my new volume, right? I added 10 milliliters of water, so that's my new volume. So if I take this number divided by 0.095 liters, that gives me 4.0 molar solution. Okay, so I rounded to 2 sig figs, right? There's 2 sig figs right there. Okay. And so it makes sense, right? I started with a 4.5 molar solution. I watered it down. It makes sense that I have a lower concentration, okay? So this kind of illustrates the idea of how watering things down lowers the concentration, and that's how we could calculate it. Okay, so that's one type of problem we might run into. Okay, but the next thing I'm going to show you is what chemists deal with more commonly. Okay, what we more commonly deal with is something that looks kind of like this diagram here. So my stock solution is highly concentrated, right? So if I've got like a big bottle of acid, hydrochloric acid or sulfuric acid, whatever, in the storage closet, it's a big container and it's highly concentrated. And if I need a solution that is lower concentration, what we do is I would pour out a small amount of my stock solution. I would put it into a container, a beaker or something, and then I would water it down and get a new solution, okay? Or I guess if there's any chemists watching, you'd put the water in first and then pour the acid in after. So if it's acid, the order matters, but sorry, I'm getting sidetracked. Okay, but my point is I take a little bit of my sample and I'm gonna water it down to get a new solution that is diluted. And so the question usually is, I know what concentration I want and I know what volume I want in the end. And the question usually is, how much of my stock solution do I need to use? How much do I need to pour in and water down in order to get the solution that I'm looking for? Okay, so let's do a couple problems like that. Okay, so let's say we want to produce a 250 milliliter solution that has a concentration of 0.01 molar potassium dichromate. Okay, so I want to make a solution, potassium dichromate. I want it to have this volume. I want it to have this concentration. Okay, but in my storage closet, I have this. I have a big container that is highly concentrated, or just more concentrated, right? This has a concentration of 0.250 molar. And so the idea here is I'm gonna take a sample of this highly concentrated stock solution. I'm gonna put it into my beaker and I'm gonna water it down until it's 250 mils, and I want to end with this concentration. So the question is, what volume of this solution, how much of this do I need to start with so that when I water it down, I end at my target concentration? Okay, so we're trying to figure out the volume of this sample that I'm gonna pour out. So there's something we need to consider between this solution and this sample, okay? What we notice is, if we think about it, I know that this concentration here, the concentration of my sample, is the same as this, right? This came from this, so it's gonna be the same concentration. Okay, great. And this concentration is going to be different from this one because, well, this one's watered down and this one isn't watered down yet. Okay, so the concentrations between these two are not the same. I also am pretty confident that the volume of this and the volume of this are not the same, because this is watered down, this is not watered down yet. But if I think about moles, the moles of potassium dichromate in this sample is the same amount of moles of potassium dichromate in this solution, right? Because I take potassium dichromate, put it in here, I'm increasing the volume, but I'm just adding water. I'm not adding or removing potassium dichromate. So this is key in order to solving this problem. So I'm gonna call this my moles, my starting moles, so I'll just call it moles 1. Okay, and then over here, the moles of potassium dichromate is, I'm gonna call it moles 2. When we think about this, we realize that these are equal to each other. The moles of potassium dichromate in this sample is the same as the moles of potassium dichromate in this sample. okay? And this is a mathematical way of representing that, okay? And that's important because we can change this equation in order to solve for what we're trying to figure out here, okay? Now, we know that based on our molarity equation, we could rewrite this. If we think about it, we know that moles is the same as molarity times volume, right? Because molarity is moles over volume, so moles is molarity times volume. So check this out. The moles of potassium dichromate here could be calculated by taking the concentration of this times the volume of this. And the moles of potassium dichromate in this final solution that I'm going to prepare is the same as this concentration times, or this concentration times this volume, okay? And I'll call that M2 and V2. So I have a starting solution and an ending solution, okay? The reason I rewrote this equation is because now I have a variable that I care about. The question is asking, what volume of the stock solution do I need to use? Well, the volume of the stock solution that I use is V1. It's right there. So I rewrote this equation so that I now have a new equation that has the variable I care about. And conveniently, what you'll notice is I know all of these numbers, right? My starting molarity is right here. Okay, I don't know V1, but I'm going to be able to solve for it in a second. And I know that my ending molarity is right here. And then my ending volume is also right here. Okay, I put it in liters, right? We want to do everything in liters. Okay, you could probably get away with not doing, if you did milliliters and milliliters, I think it'd work out, but we're going to do liters. Okay, so check it out. Now I have an equation that I can solve. V1 equals this times this divided by this. Okay, and you'll notice these two numbers are actually the same number, so this is actually a really easy problem to solve. Okay, my volume is going to have units of liters. Okay, so molarity cancels and I have liters left over. And so this translates to 10.0 milliliters. So how much of this stock solution do I need to dilute in order to get this solution? I need 10 milliliters. Okay, so I would take my stock solution, pour out 10 milliliters, dilute it with water to 250, and then I know the concentration. Okay, so the key to this whole thing is realizing that the moles in here is the same as the moles in here. And because of that equality right there, we can set up this equation. Okay, so this is going to be our dilution equation. Anytime you have a dilution problem like this, where we're taking a sample out and diluting it, M1V1 equals M2V2. Okay, so that's going to be the key there. Okay, let's try another one. Okay, so very similar problem. What volume of a 0.750 molar silver nitrate solution needs to be diluted in order to make a 250 milliliter solution that has this diluted concentration, 0.425 molar? Okay, so here we go, similar thing. We're just gonna skip right to our equation. Okay, so I'm gonna start with my stock solution, which is right here. It has a concentration of 0.750 molar. I don't know how much of it I need, but I'm gonna solve for it here pretty soon. And I know that I wanna end up with this concentration, and I want to have that volume. Okay, so it just goes in the equation, pretty easy. And then we can solve for our volume and figure out how much of this do I need to pour out and then dilute in order to get my target solution. Okay, so use our calculator. we'll take 0.425 times 0.25 divided by 0.75. Okay, and I'm getting 0.142 liters. Okay, so based on my numbers here, 3 sig figs. So there's my answer in sig figs. So this could be a perfectly good answer. We didn't specify a unit, so if you wanted to put it in milliliters, that's also fine. Okay, but both of those answers would be fine as long as the problem doesn't specify a unit. I don't really mind. Okay, so that's pretty much how it goes. Okay, so there will be probably some variations on this type of problem on the worksheet and the test, but this is the basic idea. Okay, so let me finish off with one more problem. This next problem is not necessarily a dilution problem, but it's a type of problem that's worth knowing how to do. So I think this is a good time to bring it up. Okay, another good thing to be able to know how to do. Okay, so I have 2 solutions of sodium chloride, different volumes, different concentrations. And imagine if I just poured them together into a single container. Okay, I still have a container with water and sodium chloride, right? I just dumped it all together. But I want to know what concentration do I end up with? Okay, remember the square brackets means molarity. So what molarity of sodium chloride do I end up with if I take both of these and pour them together? Okay. Well, if we just take a step back and think about molarity, we're probably just going to use our equation for molarity. Right? Molarity is moles over volume. And if I want to know the molarity of sodium chloride, what that means is I need the moles of sodium chloride over the total volume of the solution. Okay? And we're going to assume that the sodium chloride doesn't take up much volume, it's just the water that takes up the volume. So if I want the final concentration, what I end up needing is I'm going to need the total moles of sodium chloride over the total volume of everything put together. The total volume is pretty easy to calculate, right? I have a 100 milliliter solution and I combine it with a 150 milliliter solution. So you can just add the volumes together. I put them in liters, okay? We want to work in liters if we can. Now I just need the total moles of sodium chloride. Okay, I have volume and molarity here. I don't really have moles, but we can calculate it pretty easy, right? We know that if we rearrange this equation, moles just equals molarity times volume. So I can find the moles of each starting solution. I can find the moles of sodium chloride here and the moles of sodium chloride here, get those 2 things, and then just add them up to get my total moles. Okay, so if we take 0.1 liters, right, that's 0.1 liters times 0.05 or 0.5, I should end up with 0.5 moles. Okay, I'm ignoring sig figs right now. And then if I do 0.15 liters times this concentration, I get a number that I knew in my head earlier today. I can't remember it. Let me just do it real quick. 0.15 liters times 0.35 molarity, 0.525 moles. Okay, so that's the number of moles in this first solution. This is the number of moles in that second solution. And so if I want total moles, I just add them together. Right, so this is moles and this is liters. Okay, for both of those. So if I want to know the ending concentration, I just need total moles over total volume. Okay, so this is going to work out to be 0.1025 moles over 0.250 liters, which gives me a final concentration of 0.410 molar. And I believe 3 sig figs is the correct way to write that. Okay? So, again, this is not really a dilution problem, right? Notice we didn't really use this equation, right? We didn't use our M1V1, M2V2, but it's still a different type of molarity problem that we haven't gone over, so I just wanted to do it at this point, okay? So let me know if you have questions. Hopefully that was helpful. Thanks.